Great. Now we can move into the first of the three dimensions we'll talk about, which is the energy-water relationship. And we'll actually talk about that kind of three different ways. So if we subdivide it, we'll first talk about the water intensity of energy supply. Then conversely, we'll talk about the energy intensity of water supply. And at that point, we'll include wastewater treatment in the conversation as well. And then at the end of this subsection, we'll talk about the co-benefits between the two. So certain things that we can do that improve both water efficiency and energy efficiency at the same time. We'll start with this illustration from Sandia National Laboratory. The blue arrows represent water flows and the red arrows represent energy flows. Some of them are pretty obvious, like power generation requires water. When we do this in person, I point to things on the screen, so I'll have to describe what I'm looking at here. So kind of in the center toward the top of the screen, we have a power plant. So we're pulling water in from the river and evaporating it through the cooling towers. That shows, again, just illustratively how water is necessary for power generation. And the flip side of that is that water pumping and treatment and distribution requires energy. So you can see a water treatment plant over kind of from top to bottom in the middle, but over on the left-hand side of the screen, a water treatment system with energy in and water being pumped into the piping distribution up toward the city at the top of the screen. So those are pretty obvious ones, but the interrelationships don't stop there. If we look, say, at the reservoir up in the upper right-hand side of the screen, you've got the clouds delivering rain there. In periods of drought, when you have drought conditions, that can create a lack of water in the reservoir, which has what I say both a primary and a secondary effect. The primary effect in this case would be the reduction of the hydropower generation that you see associated with the dam there. But there can be even secondary effects as well further downstream. Now, if the stream flow is reduced, there may not be enough water or of an appropriate temperature to provide the cooling effect that's necessary for power generation. And that highlights a little bit about the vulnerability of the U.S. power generation infrastructure. And we'll talk a little bit more about that later because there are examples of those things happening. Now, don't be intimidated by the chart that I'm showing now. This slide can be overwhelming, but I'll discuss it, I'll explain it, and I'll really focus you just on two particular areas of it anyway. Incidentally, this is called a Sankey diagram, and it really does do a great job of showing how water and energy are both used in the U.S., because this is specifically focused on the U.S. And what's more important is it shows where they intersect. The two areas that I want to focus on, the first one is agriculture. So if you see the box, you know, I wonder if I drive my arrow around whether you even see that, but I'm kind of pointing to it now. Toward the bottom, but near the middle of the screen, left to right, shows that agriculture uses 137 billion gallons per day. And the point that I want to make there is that globally, agriculture is the largest water use. But in the U.S., it's big in the U.S. as well, but in the U.S. there is something that is even bigger from a water withdrawal standpoint, and that's thermoelectric cooling. So it's power generation, as I just mentioned. And if I drive my arrow up, again, not knowing for sure whether you even see it
We do see it, Brian. Yeah.
Okay, perfect. I'll use that then instead of having to talk about where it is on the screen. So there you see thermoelectric cooling, 196 billion gallons per day. That's the the largest category of water withdrawals in the United States. I had to pause and say that very carefully, withdrawals, because I'll come back to the difference in just a minute about withdrawals versus consumptive use. But before I do, I want to share a little anecdote with you. I live in Georgia, and that's where I'm talking to you from today, outside Atlanta. We had a very serious drought here in 2007. And when we did, we were all doing our part to take shorter showers and not water our lawns and all the conventional things. But we were also counseled to turn off our lights and set back our thermostats, which wasn't necessarily intuitive to everybody. But because of the fact that in the United States, about 2 gallons of water are evaporated for every kilowatt hour of electricity produced, it was as important to conserve energy during the period of drought as it was to directly conserve water.